Welcome everyone to the online version of the MITP seminar. Today we have David Berenstein from UC Santa Barbara, although I think you're currently visiting in Amsterdam, is that right?
Yeah, that is correct.
Okay, cool. David, thanks a lot for agreeing to give a talk, and please take it away.
Okay. Thank you, Sam. So what I'm going to talk about is a result of some works that appeared relatively recently. Last year in March, last year in November, and then a small proceedings from this year, and then some of the stuff that I'm going to talk about is still on work to appear, and that's partly what appeared in the proceedings. And that's a part of supersymmetry on the lattice. The name staggered bosons comes from some relation to staggered fermions. That becomes more clear with supersymmetry, but just let me keep that in mind. The name staggered bosons was suggested to me by people who do lattice. And then Kahler Dirac bosons are some version that supersymmetrizes Kahler Dirac fermions, and that becomes natural in that setting. So that's why that's the proper name. And then a lot of this work has been done either solo or with one of my students, Thomas Lloyd, and with Simon Cattrall at Syracuse. Okay, so where this came from is I had a conjecture about entanglement entropy in some systems that generalize the chiral boson, and I needed to do numerics, so I needed to find some discretized version of the chiral boson. The whole computation of the entanglement entropy fell through, but the discretization kind of was interesting in its own right, and this is kind of what came out of that. So that's where this came from. So let me tell you what are the characteristics. The system is bosonic and similar to how staggered fermions on the lattice work. That's why the naming. It seemed that there was a new interesting way to make gapless systems. It turns out that all the work was really being done by non-invertible symmetries in these guys. And then this segs into a lot of the work that has been going on with non-invertible symmetries in the rest of the community. And then the similarities to fermions suggest that one could look for bosonic constructions that mimic other lattice construction fermions, hence the Kahler Dirac fermions or Kahler Dirac bosons. Okay, so if you don't know what Kahler Dirac fermions are, I'm not going to have enough time to explain it. I'll just tell you quickly roughly how it works, and then I'll tell you that there's a natural way to get supersymmetry with bosons that makes it work. So these constructions actually not only lead to gapless systems in 1+1 dimensions, but also lead to theories with subsystem symmetries. So not fractals, but subsystem symmetries. I learned the difference recently. And it gives non-trivial spin chains criticality. And as I said, when they couple to fermions on the lattice, they can realize simple models of matter with supersymmetry on the lattice. And it can easily be coupled to background gauge fields and can even be put on curved manifolds, which is something that's actually interesting more generally. Okay, so the first thing I want to tell you is what a theory of a half boson is. If you start with a left-moving degree of freedom, it's a half boson in that instead of satisfying the second-order wave equation, it satisfies a first-order wave equation, and then we apply the equation of motion again, you get a half of the solutions of the wave equation. So it's the modes that satisfy the first-order differential equation are only half of the degrees of freedom of a full boson on 1+1 dimensions. It's only a left mover, so some people don't like this theory because it does not give a modular invariant partition function. However, it's a proper field theory in that, for example, the quantum Hall effect, the boundary of a quantum Hall sample, the edge dynamic satisfies the first order count. Okay.
Sorry, let me interrupt you briefly. Palab, can you turn off your audio? Can you mute yourself? Yes.
Yeah. If you're the host, you can turn him off. All good now?
I'm not the host in this meeting. I'm sorry. I think maybe you are able to turn him off.
Let me see if I'm the host.
Palab, if you can hear us, please mute yourself.
Nope, I don't have it. Okay.
Okay. Yeah, I think it's fine now. Please.
Okay. So, okay. What's this? Give me a second. I'm having trouble with my. Okay. So as I was saying, a chiral boson is half a boson. It only has a left mover, but it's a proper field theory. And there is a way to have this equation of motion be the equation of motion of a Hamiltonian system with a Poisson bracket. So if you take scalar field as a function of position, and you impose the following commutators, also known as a Poisson bracket, if you remove the
sorry, David, it seems that we're not seeing your slide. Now it's coming.
Okay.
It's come back now.
I'm going to stop share and start sharing again. What happened? Okay. Okay, let me find it. Okay. Nope. Wrong sharing.
Yeah, this is good.
Okay, is it working now?
Yeah, I think so.
So there is a way to build a Poisson bracket or a commutator algebra such that the equations of motion of phi produce the first order differential equations that I gave you before. And first order differential equations are similar to the Dirac equation. So if you take the following commutator of the phi's and you compute the equation of motion of phi with the simplest Hamiltonian you can build, which is phi squared over 2 times a numerical constant, you can see that the Hamiltonian is pretty much the most relevant thing you could possibly imagine because it's phi squared. So in terms of the algebra of the phi's, you cannot write anything that has lower order degree for the Hamiltonian. So there's no relevant deformation that gaps the system. And then one way to think about it is that if you have a left mover, there's a UV gravitational anomaly. The theory has to be anomalous also in the infrared. And then the existence of the anomaly tells you that the system will be gapless. So these commutation relations that kind of looked exotic because it's a derivative of the delta function. The delta function makes it local. The derivative makes it antisymmetric. These are actually the same thing as the C=1 chiral current algebra in positional space for the Lorentzian formulation. So if you think of phi as the J, then these commutation relations are the Lorentzian version of the current algebra for a Kac-Moody U1 current algebra. And then the derivative of the delta function is usually what's in some sense the level of the algebra. So this derivative of the delta function is a contact term and a total derivative, and this is how anomalies usually show up. So it's the Schwinger anomaly of the U1 current. Okay. So this is a well-known fact. I was just disguising it by calling it phi rather than j, mostly because I started from a first-order differential equation. Yes. Is a question? Okay. So what I'm going to do right now is give you another version of half bosons on a lattice, which are called staggered bosons. And the idea is that instead of having 2 degrees of freedom as an x and a p per lattice side, have only one. Since Q is a boson or a C or a commuting type of operator, it always commutes with itself. This is a statement about operator algebras, that any operator commutes with itself. So in order to have non-trivial commutators, if you only have 1 degree of freedom per lattice side, you need to have a non-trivial commutator with something else, and then you push the non-trivial commutators or Poisson brackets to the links of your lattice. So the idea is that instead of having local operators with a simple xp at each side, you have half a degree of freedom, and you trade the non-trivial commutation relations to the topology of the lattice, and then the Poisson brackets or the commutators are going to be the thing that induces dynamics in the system that relates the neighbors to each other. So if you make the pass, or you pass from xp to a single variable, then you need to have some type of commutator, and on a one-dimensional lattice, you basically choose a translation invariant Poisson bracket or commutator, where you talk to the nearest neighbors like x and p do. So you are, when you talk to the right, you get like p action, and then when you talk to the left, you get like a q action. And then this makes it an antisymmetric matrix. And then I have to make a sign choice of whether the Poisson bracket or the commutator is positive to the right or to the left. This is a sign choice. I just have to pick one, and I'm going to call it left moving. It's a convention. If I pick the other sign choice, it's a right mover. And I can pass from a left mover to a right mover by a canonical transformation or by a change of variables. So it's not intrinsically different to choose one sign over the other one, but I have to pick one. And then the really important thing is that this Poisson bracket looks like a derivative of the delta function in discretized form, where this would be like a discretization of the derivative of the delta function, where you're just talking to the 2 nearest neighbors. Okay. So the half boson is similar to a half fermion in that the degrees of freedom are distributed between neighbors on the lattice. A half fermion is technically a Majorana degree of freedom on the lattice. And if you take a Dirac fermion and split it into Majorana fermions, in the staggered formulation, you get different components of the Dirac boson, of the Dirac fermion into different lattice sites. So this is similar to a staggered fermion formulation. There's some Majorana fermions, building a Dirac boson, and hence the name staggered fermions. And as I said, for fermions, staggered fermions in 1 + 1D are also Majorana fermions. And Majorana fermions have a whole bunch of topological properties discussed by Kitaev that are very interesting. So a lot of the Majorana wire story. So here we're constructing something with bosons that has some similar flavor to the staggered fermions.
David, can I ask a question?
Yes.
So is there a reason for choosing the symmetric difference? Could one choose forward or backward difference?
Yes. Well, you have to pick a sign. So the Poisson bracket or the commutators need to be antisymmetric. So if you pick it to be +1 with the right partner, translation variance tells you it has to be a -1 with the left one. So this is a statement, the fact that it's +1 and -1 is a statement about the commutators needing to be antisymmetric and translation variance requiring that these two be related to each other.
Okay, Thanks.
So once you have a Poisson bracket matrix, it's constant and antisymmetric, and therefore it defines a phase space, meaning that it satisfies all the conditions that you need to define some quantization in terms of, you know, free variables. Now I copy my Hamiltonian. So I had a Hamiltonian in the continuous variables. So I'm going to make the simplest Hamiltonian that I can imagine in terms of these Q variables, which is just the sum of the Q squared. This is quadratic in the Qs. And then when you compute the equations of motion for Q, you get that Qi dot is Qi plus 1 minus Qi minus 1. And the sign choice tells you that it's plus Qi plus 1 and minus Qi minus 1. And then when you look at this, if you take the naive kind of continuum limit of long wavelength expansion, then you look at something that has a Q dot approximately equal to twice the derivative of X with respect to Q. So it's as if you constructed something that satisfies a first order differential equation with the speed of light being equal to 2. Okay. So the claim is that this Hamiltonian, at least naively, produces equations of motion that are first order and look like the wave equation. So it looks naively like it discretized the problem that we needed to discretize. If you actually do the mode expansion, so you do Fourier imposition, you can determine completely the dispersion relation. So the frequency as a function of k is minus 2 sine of k. Really important thing is that since we had a first order differential equation, omega is a single valued function of k. The minus 2 sine k is just what we get. And then if you look at the Nielsen-Inomiya argument, which is the one that is used to predict doublers in systems with fermions in various dimensions, here we have that the low energy physics, meaning omega equal to 0, there's two crossings of 0, omega equal to 0 at k equal to 0, and omega of pi equal to 0. So you get two crossings of 0. And one of them is a left mover and the other one is a right mover. And you compute which one is left mover and which one is right mover by taking d omega dk at the crossing of 0. Because the system was free, in the sense that you get linear differential equations, it is straightforward to quantize. Whether something is a raising or lowering operator depends on the sign of omega k. And the mode at k is conjugate to the mode at minus k, and k is a periodic variable in the sense that k is equivalent to k plus 2 pi. Okay, so the claim is that you take the system, you get a bunch of free bosons, and then you get two crossings of 0, which means that the omega of some values of k vanishes, meaning that the theory is gapless. So in the infrared, you get left movers, and they're roughly ferromagnetically ordered, meaning that a left moving function will produce an excitation where the amplitude of the nearest neighbors are aligned. And then for the right movers, you're at k approximately equal to pi. And at k equal to pi, the amplitudes are approximately anti-aligned. So if all the things point in the same direction, they're ferromagnetically like ordered. And if they're all pointing in the opposite direction, they're anti-ferromagnetic or nil ordered. So the claim is that the magnons of this system, some of them are ordered. These are the left movers, and the other ones are anti-aligned, and then they're nil ordered. And now, if you take this system and you deform it by, or you do perturbative computations on top of it, when you do perturbative computations, so long as you keep translation symmetry, omega of k will keep on being a single valued function of k, so long as your quasi-particle picture is a good picture. And therefore, if it is positive at some value, because of k goes to minus k being conjugate modes, then omega of k will also be negative at some other values. And then the crossings of 0 have to persist. So perturbations do not modify this graphic particularly, and on top of that, precisely where the zeros are will actually stay fixed because of how the systems are constructed. So the claim is that this theory is gapless, and one can have a very cheap topological argument that says that the theory stays gapless even after small deformations because so long as you keep the translation invariance of the system, the left movers and the right movers are at different places in the Brillouin zone, k equal to 0 and k equal to pi, and these crossings of 0 will not be cannot be just wished away. You have to do a very large deformation to get rid of it. Okay. If you do a canonical transformation where you change the sign of the Q's on all the odd sides, then the left moving Poisson bracket becomes a right moving Poisson bracket, and it changes all the signs in the Poisson bracket. So it shows that both formulations are equivalent to each other, at least on an infinite line. So the symmetry protection, the massless bosons are protected, even in the presence of perturbative interactions. I already said that. So the claim is this is a way to build gapless theories, even if one deforms the physics of the system. When you take the theory on a large lattice of finite volume, the K becomes approximately quantized, or K is quantized as 2 pi n over L, and the frequency becomes approximately linear in K. So you actually get a conformal field theory with only one positive frequency mode per n equal to 0, and a similar story for K approximately equal to pi. So you get two types of modes. You get left mover and a right mover set of modes. And you basically have a critical theory with central charge equal to 1. The important thing is that on an infinite line, there's two elements of the algebra that commute with everything. So there's two central elements. You take the even and the odd sums of the Q's. You can show that they commute with everything. This is one way to think about them as zero modes. When you quantize the system, because they commute with everything, the equation of motion of the C even is that it stays constant, and the same for C odd. So once you fix the value of C even and C odd, you can forget about them, and then the rest of the modes will behave like usual. But they're central elements of the commutator algebra. So this is not a traditional Poisson bracket where the system is non-degenerate. There's these infinite sums that produce some degeneracy or produce some odd behavior of the system when you quantize. And then when you put it on a finite periodic lattice, if you have an even number of sites, then if you pick periodic boundary conditions, then you keep the distinction between the even and the odd sides. And then the sum over the even sides is central, and the sum over the odd sides is central. So you can get two zero modes when you use periodic boundary conditions. And if you choose anti-periodic boundary conditions, which is a statement that can be put inside the Poisson bracket, then you get no zero.
Sorry, David. It seems again. Oh, now so the slides sometimes go black and then they come back again. So now it went black for quite some time, but now we can see it again. I'm not sure. I think it should probably be something on your side, but I'm not entirely sure what.
I'm not seeing anything, but there might be.
Now I can see. It's sort of periodic phenomenon. It goes off and then comes on again.
Is it every time I change slides?
I haven't. Now we can see them. Yeah, now we can see them. Maybe I'll give you a shout when it happens again. Okay.
Okay. Very good. So, so the important thing is that if there's a zero mode at K, there's another zero mode at pi minus K. So at K equal to 0 or K equal pi, there's two zero modes. And then if you take either the red or the blue system, it is reflection symmetric around a reflection about the vertical axis.
Yeah, now it happened again. Is there something specific that is happening on your computer by any chance?
Nothing. Absolutely nothing. My computer is fine.
Your computer is fine.
There might be
Maybe
latency. It might be a local internet here, but I'm not seeing it.
yeah, maybe one thing we could try is so when you share your screen, you're only sharing the PowerPoint, right? Or
Yeah, I'm only sharing the PowerPoint. I'll tell you what. I'll stop my video, and then maybe that will help.
Yeah, maybe one thing I was thinking, maybe it helps if you share your entire desktop and then just maximize your screen.
Okay, let's try that again.
Sorry about that.
No, it's okay. Share screen up, the whole desktop. And then let me go to my.
Yeah,
Okay.
Let's try it like this. Yes.
Okay. So the point is that if you're in an even lattice, you get two possible boundary conditions, periodic and anti-periodic, and then that are compatible with the system. And then if you pick any of these two, you get a ground state, which is parity symmetric, no matter what the choice of the two symmetries are. And the parity here is a statement about k going to pi minus k. So if something is a raising operator and k is positive, pi minus k is also a raising operator. So this is a system that relates two types of raising operators to each other. And then this system is well behaved and it has two zero modes. And if you take an odd number of lattice sites, then you have to distribute your k. So maybe I didn't make this clear. The circle over here is really the fact that k is periodic, so you have to follow the circle around. And that's kind of the angle, the angular direction is k on the circle. And then I have the zero of energy over here. So energy is the vertical axis. And then k is around the circle. If you actually use an odd number of lattice sites, then you have an odd number of k. You have to distribute an odd number of vertices uniformly on the circle. And then the statement is that if you have a zero mode at k equal to 0, at k equal to pi, there's no zero mode. So the notion of modes near k equal to 0 becomes different than the notion of modes near k equal to pi. On the left movers, let's say if it's the one where you have a zero mode, they're integer spaced. On the right-hand side, the differences between them is integers, but they're at half integer values. So for right movers, the notion of mode n is a half integer. So there's no relation between the left movers and the right mover mode structure. So parity is broken in that the left movers and the right movers are not talking to each other. And one of the reasons this is going on is that if you have a non-degenerate Poisson bracket, then you require an even number of variables. If you have an odd number of variables, there's always one degeneracy or an odd number of degeneracies. The number of zeros of an antisymmetric matrix of zero eigenvectors is always an odd number if the matrix has an odd number of entries, or is an odd matrix. So the statement is that there is this weird statement that when you try to take the theory at finite volume, whether you have an even versus an odd number of sites, you get different physics on the system. And whether you have an even or an odd number of sites, that would be something that should come from the UV and should not have any relevance on the infrared, but it does matter in the infrared. So the infrared dynamics is sensitive to properties of the lattice in the UV that are not apparent in the continuum limit. They survive as the choices of boundary conditions of left versus right. Okay, if you do things on an open interval, if you have an odd number of sites, there'll always be one zero mode, and these like Neumann boundary conditions. If you have a even number of sites, There's no zero modes. It's like Dirichlet-Neumann boundary conditions. And these are very similar to the counting of zero modes for Majorana fermions. And the reason is similar. When you try to pair Majorana fermions to get a frequency or mass, the mass matrix for the Majorana fermions is an antisymmetric matrix. So if you compare these to the Majorana wires, in the Majorana wire story, whether you have Majorana fermions or not at the edges is related to whether there's an even or odd number of sides in your Majorana spin chain. So it's similar to the story of Kitaev. And the math, at least from the point of view of the matrices, is the same. Okay. So now let's talk about translation symmetry, because there was something weird about the fact that even versus odd number of sides makes a difference. So let's try to understand that. So the big question is, when I take the QJ and I go to QJ plus 1, is it a symmetry? And it might not be a symmetry in the sense that we're used to. It's definitely a symmetry of the algebra of the Qs. But the problem is that when you take QJ to QJ plus 1, we have two zero modes, the C odd and C even. So it turns the zero mode or the central element of the even sides into a central element of the odd sides and vice versa. So the statement is that although this is a symmetry of the algebra of operators, it turns out that this is not a symmetry that you can realize as a conjugation by unitary in the algebra itself. It's an outer automorphism of the algebra. So from the point of view of representation theory, it's not clear that this symmetry of the algebra can be extended to a symmetry of the Hilbert space of states. When you have the oscillators, so the things that are not the zero modes, there's a theorem called the Stone-von-Neumann theorem that tells you that you have canonical commutation relations, also known as the Weil algebra. There's a unique irreducible representation of the Weil algebra, and it can be extended to many bosonic variables that satisfy copies of the Weil algebra. So if you have something that satisfies the Weil algebra and you land on something that satisfies it, you can upgrade whatever action you had to a unitary action on the Hilbert space. However, this is not necessarily true for the central elements, because if the elements are central on irreducible representations of the algebra, the C odd and C even become C numbers, and it is not automatically the case that C odd and C even will be mirrored in the full Hilbert space of states. Some values of C odd might have a C even that they can match to, meaning when you swap C odd and C even, there might be a conjugate pair, or there might just not be such a state. So even though it is a symmetry of the algebra, it is not necessarily a symmetry of the representation theory. So when you put whatever your Hilbert space is, meaning you take all the values of C that you have and sum over the representations that you're given, you don't have a guarantee that it's a symmetry of the representation theory. On the other hand, if you act twice, you send the two central elements back to themselves. So there's always a candidate for the action of the symmetry on the Hilbert space. So acting twice, so instead of taking a step of one, taking a step of two, is something that is like a standard translation in a conventional theory. So there's a difference between acting once and acting twice that makes a difference. Acting twice is like a regular translation symmetry, and acting once is something that's not quite like a translation symmetry. So there's two types of system, or two types of symmetry. There's a translation symmetry, which is acting by two, and then there's also acting by one, which is like a type of square root of the translation symmetry. Okay, so this acting by one, or moving by only one in the Hilbert space, can only be considered a symmetry on the subsector of representations where the even and odd modes of the central elements can be matched. So in practice, since this can only be a symmetry on a subsector, you basically first write a projector that projects to the shared subspace of matched zero mode pairs. And then when you don't have a matched pair, you call the projector equal to 0. And then you call D the half translation where it makes sense. So it is on the subspace of the Hilbert space where the projector acted non-trivially. Okay? So this translation by half symmetry acts only on this subspace and still commutes with the Hamiltonian. And the idea is that this object, whatever it is, this translation by half, is basically really built after projecting onto the shared labels. So when you square D, you have the projector, and then you have translation by 2, which is the translation symmetry that I told you could be put together into a unitary symmetry. So the claim is that to build the symmetry algebra of the system, translation by half is a symmetry that commutes with the Hamiltonian and that squares to the regular translation composed with a projector. And the projector is this projector that projects onto the even and odd central elements, having a mirror pair somewhere in the subset of representations. Okay. It's a very long-winded way of saying that I actually have a non-trivial symmetry over here, and it's one of these non-invertible symmetries. And it's non-invertible because it's clearly not a unitary on the Hilbert space of states because the projectors can never be inverted. Okay? So when you see algebras like this, that something squares to translation times a projector, that's the hallmark of non-invertible symmetries. So this system that I pulled out of a hat ends up having a non-invertible symmetry. And then our question right now is to ask, what is this non-invertible symmetry? So if you have a non-invertible symmetry, that usually leads to gapless theory. So it suggests that it's exactly this non-invertible symmetry that's doing all the work. And I just told you that translation by 1 is this weird non-invertible symmetry, and translation by 2 is like an ordinary translation symmetry. So translation by 1, which is what I was actually using to, or translation invariance and the translation by 1, which is what I was using to make a statement about the dispersion relation, needs to be related somehow to the fact that translation by 1 is not really a standard symmetry in the system. So it's this non-invertible symmetry that's doing all the legwork. I just didn't know when I wrote the first paper that this was a non-invertible symmetry. Okay. So once you have this statement that you have a non-invertible symmetry, you want to see if you can build the half bosons from a regular boson and try to understand what that non-invertible symmetry is in a more conventional setting. So I want to rebuild this commutator algebra from a regular boson. So the idea is that if you have n bosons, then you have n x's and n p's, and then from n x's and n p's, you can build 2n variables, so that's 2n q's. So my goal is to build from n copies of x and p, 2n variables q that have the same commutation relations that I gave you before. And one way to do it is to take the even q's to be the p's, and the odd q's to be the differences of the x's between the nearest neighbors. If you take the commutators of the q's built this way, you can verify that it satisfies the same commutation relations I gave you before. But beforehand, I told you that there were 2 central elements. And here I started with a non-degenerate theory between the x's and the p's. So there should not be 2 central elements, things that commute with everything. So when you go from these n variables to these 2n variables, you've done something funny. The map is non-invertible. Okay? So to go from a non-degenerate bracket to a degenerate one, I threw something away. And then what I threw away is the notion of the center of mass of the q's. So if you think of the center of mass of the x's as a variable, I only took the differences, the relative distances, but I threw away the center of mass degree of freedom. So I threw something away. And in throwing that thing away, it turns out that I went really from 2n variables to 2n minus 1. And then, of course, I get at the general Poisson bracket because I start with an even number of variables and now I have an odd number of variables. So there is a central element, which is the sum of the even q's. That would be the center of mass momentum, the sum of all the p's. But I don't have the center of mass coordinate, which is the sum of all the x's. So the statement is that I went from 2n variables to 2n minus 1. I preserve the center of mass momentum, but not the center of mass position. So the zero mode for dot q is missing. And then what I'm going to do now is tell you that the Poisson bracket of the staggered bosons is built by adding a new variable, which is central and will correspond to the sum of the Q2I being odd on a periodic lattice being non-trivial. So I'm adding something that if I just take this at face value and I sum the odd Q's, I will get 0. Here, I'm going to insist that it's allowed to be non-zero, and moreover, that I'm allowed to set it to a constant. So if I set the Q2I to a constant, what that means is that xi plus 1 minus xi is shifting by regular intervals. And if I'm in a periodic lattice, and if I come back, xn minus x0, they differ by some fixed amount. So I'm coming back to x with a shift. And coming back to x with a shift is what we call winding. So the zero mode for q, if you add it, for the odd q, if you add it, is like adding classical winding to the variables of the periodic lattice. So the claim is that the system adds a new variable, which is kind of the central element, roughly speaking, which tells you that the Q2I plus 1 become unconstrained under this commutator algebra so that the sum of the Q odd is not 0. You just relax that constraint. And then what you're adding corresponds exactly to the winding of the variables in a periodic lattice. So the claim is that you kind of not quite go from a boson to a half boson. You go from a boson to a half boson on a lattice twice the size, and you have to tweak around the variables a little bit in a way that in some technical sense is non-local. Okay. So what is translation by 1? If you take it at face value, it sends p to x and xi minus 1 to pi plus 1. So what it's doing is it's sending the derivative of the position or x dot to the gradient of x or to the gradient of the field, phi dot to gradient of the field. And it's sending the gradient of the field to phi dot. So this is exchanging the notions of winding and momentum. And in CFT, this would be T-duality. So this is a discretized version of the T-duality. So translation by 1 is T-duality. So what is T-duality? When I was in grad school, T-duality on a lattice, not on a lattice, but on a conformal theory, is not really a symmetry. It's an equivalence of two theories. You take, let's say, a theory at radius r, and a theory at radius 2 over r, and then the partition functions and correlation functions can be related from one to the other. But doing the same translation twice is what preserves the usual symmetry. It kind of takes you back. You do T-duality twice, you get back to the original theory. But what we're doing here is T-duality, and then T-duality is not a symmetry, so why should T-duality be a symmetry? T-duality cannot really be a symmetry on its own. What you can say is that when you apply T-duality, you have two conformal field theories. They have a spectrum of operators on each one of them and a spectrum of correlation functions. And there might be a subset of operators and correlation functions that match across them. So on that subset, when you project to that subset, then you could get an equivalence of the two subsectors of the theory. And that's what this projector that shows up in non-invertible symmetries is really doing. So you make T-duality into a symmetry by first assuming that the C labels, meaning the left movers and the right movers zero modes, well, they should form a lattice like the free boson, and that given a pair of labels C, there's a unique irreducible representation. And then you apply the duality or the transformation to the maximum set of paper labels that are mirrored, and you say that acts as a symmetry on this subsector. So this requires that the theory and its T-dual have some relation between the radii to have a non-trivial relation between winding and momentum and their energies. And then you extend by zero everywhere else, and this is the non-invertible part. So the idea is that the theory and its T-dual need to be related in some way. And if you do that, then T-duality can be converted to something that becomes translation by two, which translation by two on the continuum limit becomes the identity operator, and then there's a projector onto match labels, and this is the typical thing that shows up in these setups. So one more thing is, where did modular invariance come from? Since I broke everything, I have to put it in by hand in the large volume limit. I have not really described the origin of the quantization of the c-values. So if there's time and somebody really wants to ask, you can ask me afterwards. But at this point, I don't really have an idea of how to make it work. So we can restrict ourselves to consider lattices of charges that are compatible with a free scalar, or we can restrict in some other way. So if we revisit all the gaplets in story, the argument I gave was based on single valuesness of the dispersion relation, but this is really in secret a double cover of the regular Brillouin zone, because in the regular translation by 1 in the XP lattice becomes translation by 2 in this system. So this double cover means that when I go to the half P, this is acting by one value on the left movers, and it's acting by a different value on the right movers. This is the -1 that distinguishes left movers and right movers when you do T-duality. And then in the limit of zero quasi-momentum, you get mapped to different points on the double covers. And this -1 difference in the square root is exactly the statement that T-duality acts by -1 on right movers and is the left movers intact. So the claim is that the reason why this was working was that if you go back to the original theory in terms of the regular scalar, this was a non-trivial T-duality symmetry, and then the non-invertible symmetry of the system is at the root of the system being gapless. So this is the statement that this double cover of the Brillouin zone is really a secret story about non-invertible symmetries in disguise. Okay, so now that you have this theory with a commutative Q variable at each side with non-trivial Poisson brackets, I want to go to theories where the variable Q is not something that can take a continuous spectrum, but something that's better behaved from the point of view of quantum computing, meaning that in principle, I can accommodate it into qubits as opposed to an infinite Hilbert space. When I do that, I need to play games. So it turns out that the symmetry algebra of the Qs also has a symmetry of translations in target space, meaning that the Qs, if I shift them relative to each other by C numbers, they still satisfy the same commutator algebra. So I can gauge all these translations of the Q variables. So I'm going to go straight to a set of invariant, gauge invariant variables of the Qs, which is these exponentials of the Qs. And if I pick some periodicity for the little Qs, I get some K that is fixed by that periodicity, which basically is fixing alpha.
Sorry, David, can I just ask one question about the previous?
Yes.
So you mentioned that this non-invertible symmetry is a bit like T-duality, right?
Yes.
But what now is exactly the step? So as you also explained, T-duality relates to different theories.
Yes.
Or equivalence between two different theories. So I just missed maybe, or could you explain again how I should think about this non-invertible symmetry? That I should think as a symmetry within a single theory, right?
Yes.
Or
the point is that there's this projector.
Right.
So when you say there's a projector, you're saying T-duality, which is something that I would in principle do to relate to theories.
Yeah.
I'm trying to relate one T-duality and the operators in the new bases to the same operators in the same bases as I had before. But that's not usually allowed unless there's some special condition that says that a subset of the operators can be mapped into itself. Okay? So I will get more precisely to what this means in practice a little bit later on when you understand what the projector is. Because the whole thing is, what is the projector really doing? That will be the thing that will clean it up.
Okay, thanks.
Okay. So this will be cleaned up by this problem. So once I go to these variables, I can get, I can compute the commutation relations of the case. Because these are exponentials of the Q's, I can use the Baker-Campbell-Hausdorff formula to construct them, and then I'm going to get some, phase that relates one ordering versus the other ordering, and then the phase is roughly exponential to the I alpha squared. So alpha is real, this is a unitary number, and then something nice happens if omega is a root of unity, because then if I take an nth power of ki, it becomes a central element of the full algebra, and therefore I can declare that central element to be identically equal to 1. So what that means is that instead of having an infinite algebra of the case, I now have a finite algebra where each k can only be taken up to an nth power. And when I take that nth power, then I get back to the identity, and then everything is good. So I get a finite algebra as opposed to an infinite algebra. And therefore, because the algebra is finite dimensional, all its representations are finite dimensional, all the irreducible ones. And then, as I said, my main reason was quantum computing. If it's finite dimensional Hilbert space, then I can put it on qubits. You can take the map that I had of the P and the X's to exponentials of the I alpha P and exponential to the I alpha gradient of X. And then if you think of these as doing periodic identifications of P and X, I'm writing things on a torus. And then these commutation relations become these kind of clock shift matrices commutation relations that are well known and show up in other places in physics. And then if you think in terms of those, these K2I become these Q operators, and the K2I plus 1 become P cross P inverse operators in between different lattice sets. Okay. So the claim is that this algebra that I did, it preserves the commutation relations. So I can write also a Hamiltonian in terms of the case that is invariant on the translations by 1. And translation by 1 is my old non-invertible symmetry. So I can basically write systems that preserve the non-invertible symmetry and Hamiltonians that preserve it.
Sorry, David. Sorry to interrupt you again. Can you just quickly? I've heard of the clock shift matrices before, but they're not completely. Could you just briefly explain what they are again?
Yes. Let me do it this way. The clock shift matrices, roughly Q is 1 omega squared, etc. And then the P behaves like 0, 1, 0, 1, 1, and then it's also unitary, so it goes over here. And then 0 over here. Okay. So what happens is that P moves by 1. So you have the standard basis acting with P, takes E0 to E1, E1 to E2, E2 to E3, or something like that. And then Q multiplies each of them by a phase. So the shift means that the E's get moved into each other, and the clock means that, each one of them has a different phase. There's some conventions over this stuff.
Okay. I think that helps. Thank you.
So I'm going to close the whiteboard. Can you still see my screen or not? No. Okay.
Now we can't see your slide yet.
Okay.
So
What I do with it? Okay, what I do? Can you see it now? No.
no, not yet. Yeah, now we can. I can. Yeah.
Okay. So as I said, you can turn it into a problem of clock shift matrices. There's slight generalization of polymatrices. So, okay. Let me do something. This thing broke down somewhere over here. Okay, I'm gonna go again because it broke my cursor key. Now I'm gonna share the full screen again. And then, okay, all good now?
Yeah, all good, all good. You have about 10 minutes to
Yes,
to
okay, so it's gonna be fun. So what happens is that you get a system. Now you take a new Hamiltonian, which is the sum of the k's plus the k inverse, because you have to make it self-adjoint. But the point is that the translation by 1 was preserved. So you send k to I to k to I plus 1. So that is a symmetry of the Hamiltonian, and that was my original non-invertible symmetry. So the px variables became periodic, and we can read the periodicity from k being single-valued. And if you try to understand the quantization condition that you get for the zero modes at the level of free field theory, in conformal field theories, you come up with something that's square root of 2n. So this is a statement about how the periodicity of the zero modes that you inherit becomes reflected in the radius of a conformal field theory. And then the spin chain Hamiltonians, which are this kind of sum of k plus k inverse, which is guaranteed to give you a Hermitian Hamiltonian, becomes a spin chain of these Q and P matrices. And these are called critical clock model spin chains. And then our goal is to understand what happened to the non-invertible symmetry. So what happens here, if you actually look at what you get, is that if you have omega equal to -1, then the clock shift symmetries are 2x2 matrices, they're polymatrices, and then this Hamiltonian is criticalizing in a transverse magnetic field. If you do 3x3 matrices, you get 3-state Potts models as criticality. And then for n bigger than 3, you get spin chains at criticality with central charge equal to. So after n equal to 5, things are well behaved, and actually you get systems with a U1 current algebra. So you inherit the symmetry that you had in the UV of the X's and P's or the Q's directly. So what happened is that translation by 1 persisted. We did the same on all lattices of the Q variables, and this was our non-invertible T-duality symmetry. So what happened is that the symmetry in the new variables that changes Q to P cross P inverse is what people call the Kramers-Vannier duality. It's also a non-invertible symmetry, and the spin chain landed at the self-dual point, meaning at the place where the Kramers-Vannier duality is actually a symmetry of the Hamiltonian. And then in a bit more detail, the product of the Q's is a symmetry, and Q to the n is equal to 1, so you have a Zn symmetry. And when you map the Q's to the P cross P inverse, the product of the Q's needs to be the product of the P cross P inverse. It needs to land on something that has trivial symmetry. So the projector needs to map onto systems that have trivial Q quantum numbers. So you have to go to a Zn invariant state. So the statement about the Kramers-Vannier duality is that the projector is the thing that projects you onto the Zn invariant states of the theory. So one way to think about it is that T-duality, which was our Kramers-Vannier duality, is equivalent to a Zn orbifold projection. So if you say that a Zn orbifold is equivalent to a T-dual, those are two operations that I can do on conformal field theories, and that lets me find the radius of the system. And when I do that, the radius of the system ends up being the square root of 2n. Okay? So when you have central charge equal to 1, and when you have a current algebra, and with modular invariance, and when you take the long wavelength limit, meaning t goes to 1, this d squared projected to equal to 1 is the thing that tells you that in the radius is t dual to an orbifold, and that's what lets you determine actually the radius in conformal theory. So now you're saying that two different operations take you to the same theory. One is t duality, which is a symmetry, and the other one is an orbifold, t duality, which is an equivalence of two theories, and the other one is an orbifold, which is another operation that you can do on field theories, which usually takes you to a different field theory. So if the two take you to the same place, that gives you a relation between the radius and the t-dual radius. Okay, so this is how you get the quantization from using this symmetry. Okay, people have done it numerically. People report the same result numerically with the emerging methods, and we also did exact diagonalization on a very small lattice and found the same. Okay, now you can ask, if you're in this conformal field theory and you have this symmetry, since the lattice in the UV is not conformal, you might have some deformations of the theory, but they have to be Zn invariant. And then they also have to preserve the non-invertible symmetry. And then you find that in this theory, the operators that you're allowed to have that satisfy all the symmetry conditions start with conformal weight n quarters, and then this become irrelevant when n is bigger than 4, and that explains why in the UV it flows to the theory that we wanted in the infrared with central charge equal to 1. And when n is less than or equal to 4, first you're allowed a marginal deformation, so you find a theory that does not have a U1 current algebra, but it has the same central charge. And when n is less than 4, you have a relevant deformation, so the theory flows to a non-trivial conformal fixed point with central charge less than. Okay. And then this is what explains all this strange behavior at n less than or equal to 4. Okay. If you use a slightly different normalization for the non-invertible symmetry, this is what people call the Tambarana-Yamagami categorical symmetry for the group Cn. Okay. So this is basically what that is. I'm going to skip this stuff. I'm going to go straight to supersymmetry. And I'm going to tell you that you can do something that's similar to how Kahler Dirac fermions work. So this was similar to staggered fermions. Now I'm going to show something that's similar to Kahler Dirac fermions. Kahler Dirac fermions can be put on any triangulation of a manifold. The fermions behave like forms. And the action, in our case Hamiltonian, is built from the triangulation complex exact sequence. This is something that you just need to know. So what I'm going to do is basically say, how can I make this work? I'm going to take a commutator bracket for bosons that follows the information of an exact sequence associated to a complex or a triangulation. The triangulation of a manifold will give you a boundary, and then the boundary of some triangles is another set of triangles, and then there'll be integers. If you use CW complexes, the boundary of a cell is n-1 dimensional cells with some integer coefficients. So what I'm going to do is I'm going to write one bosonic variable per cell complex, per cell in the complex of the different dimensions. And I'm going to require that the commutators of the variables follow these same integers. When I do that, I can build a simple Hamiltonian. And then what I'm going to show you is that this Hamiltonian that I just built from some weird set of commutators will have some interesting properties due to supersymmetry. So Kahler Dirac fermions have the same data for each cell. You have a Majorana variable that anti-commutes with everything else. So the idea is I'm going to build a supersymmetry, which is I sum over the bosons and the fermions just naively. And if I square Q, when the thetas are equal to each other, theta squares to 1 because they're Majorana fermions. And then I get xk squared. That's my bosonic Hamiltonian. And when the thetas are different, then I get them in two possible orders. And when I get them in the two possible orders, I have to order them in the same order. And then that produces a minus sign in one xk tilde versus the other one, and that produces a commutator. So the commutators of the x's produce information about the complex of the triangulation, and this is exactly what goes into the symmetry or into the Kahler Dirac Hamiltonian. So when you get Q squared, you get the bosonic variables give you phi squared, and the fermionic variables gives you this antisymmetric combination over here, which is exactly what shows up with Kahler Dirac fermions. So the claim is that this city supersymmetry gives you the Kahler Dirac Hamiltonian plus superpartner bosons. So the Kahler Dirac Hamiltonian for the fermions gets partner into the bosons, and this is why this will be called Kahler Dirac bosons. And the claim is you get really nice supersymmetry. So if you have more general theories, you can allow twisting by global symmetries, meaning you get the commutators of the phi's. You're allowed to put whatever U's you want in here, which include the background lattice gauge fields that live on the links. So the claim is that you can basically upgrade these to more systems and study supersymmetric matter coupled to a background gauge field. Okay. It squares to the correct Hamiltonian. And as I said, it squares to the Kahler Dirac Hamiltonian for bosons. So if you do this in 1 + 1 dimensions, you get the same, you get that the Kahler Dirac fermions are Majorana fermions, and the Kahler Dirac boson is this boson that I had before, which was the staggered boson. And the Majorana fermions are also known as the staggered fermions, so the staggered fermion and the staggered boson show up the same way. And then if you add a little bit of noise, the theory is still critical. And then you can also do this with supersymmetry. And then when you do that, you can get more information of the system. So the zero modes are preserved, and the low frequency modes become delocalized, and the high energy modes are very localized. The log of the amplitude kind of decays exponentially on the sidelines. In any case, the important thing is that this is the really important thing is that the zero modes are preserved on an even lattice. You have two exact zero modes still, and then that will also be translated to the fermions. So this preserves the supersymmetry at the level of zero modes. It's still critical with double degeneracy from left and right movers, and then you'll also get the fermions. You'll get this paired to the fermions. Okay, so the idea is that you can get supersymmetry, and some of the protection of the symmetries kind of persists even when you add a little bit of noise. The rough reason is that if you really think of phi as the derivative or as the current field, adding a perturbation with a stochastic noise on eta is like adding a random perturbation proportional to a stress tensor. That's basically like coupling to a non-trivial metric in 1 + 1 dimensions. Okay. I'm going to skip that. I'm just going to tell you the conclusions. We got some novel constructions of lattice algebras that have non-trivial commutators between neighbors. They automatically realize non-invertible symmetries and immediately lead to interesting models that include critical spin chains, not fractals, but systems with non-invertible symmetry, and models that are similar to discrete gauge fields. I skipped that, but I'm just telling you the answer. Staggered bosons are really similar to staggered fermions, and when you put them together, you get SUSY on the lattice on the nose with staggered fermions being paired exactly to staggered bosons. So that makes them even more similar to each other. And that's that.
All right, thanks, David. Let's thank the speaker. Are there any questions? Maybe I can start with a question, David. At some point you mentioned, so I think when you were going to the shift and clock variables, you're somehow motivated by having this map to a qubit system, right?
Yeah.
Could you expand a bit more on that motivation? Are you looking to are you looking to literally implement these models on a quantum computer, or is this? Yeah.
So the statement is that it's self-serving in the sense that I do have funding to study how to put quantum theories on quantum computers.
Okay.
And then the question is how to get interesting quantum field theories on quantum computers that I would care about.
I see. I see.
These came from trying to understand how to get models with conformal symmetry or models with gapless systems. And when I started this, I still didn't have the quantum computing angle completely yet, but I did need to discretize some of these things anyhow. And then that kind of makes it even more coincident. So part of the reason is really trying to better understand how to put relativistic quantum field theories on quantum computers. And to be relativistic, it kind of needs to be gapless in some sense, because I cannot put the Lorentz group, which has infinite dimensional representations, on a quantum computer. So I have to look at lattice systems where the infrared physics becomes Lorentz invariant. So the main interest is to look for things that are gapless or neatly gapless near phase transition.
I see. Okay. Okay. Very good. Thanks.
The other thing is putting things on curved manifolds is not trivial. And then if you can put it on the lattice on a curved manifold and it still preserves all the symmetries, it becomes really, really interesting, which is, a lot of theories we study with continuum methods. You study the system on a non-trivial curved manifold, and you can get a lot of information about the field theory based on that. Z functions and all kinds of things. We need to be able to do the same with quantum computers. And it's only interesting if whatever you do has a nice story for the continuum limit.
Right.
Can you hear me?
Yes.
Can I ask a question? Well, two questions. The one question is, suppose I just have regular bosons on lattice sites, or X and P's on lattice sites.
Yes.
Is there a way to construct these staggered bosons from those ingredients?
Yes. The statement is that the staggered boson is constructed. Let me go back to the slide, and let me share the slide. Okay, where is it? Okay, here we go. So I'm going to share my slide. Okay. This projection is the construction of the staggered bosons from the regular bosons. You take the regular bosons, you have to double the lattice.
Yeah.
And then you have an
Okay.
even number. You pass the even numbers to Q2i's and the odd ones to the differences. And then you add one extra variable, which is kind of like this, the winding number.
Yeah.
Now, if you allow defects, like we do in conformal field theory sometimes, or defects in these lattice systems, there's defects that can realize the additional pieces that you need to make sure that you actually land with a full set of degrees of freedom, and that have all the information. So this is something I have in progress, and I haven't finished doing all the computations, but in principle, you can do even better. So you go from nxp to 2n minus 2, and you do some extra things with the other two to kind of get rid of some part of the XMP and make sure that you get the correct lattice algebra with the full set of even Qs and odd Qs and zeros.
But isn't this just sort of having springs that are connected to each other? I mean, to have so that it's the displacement xi plus 1 minus xi that's important, rather than xi and xi plus 1 on their own.
Yes. So the point is that if I give you the projection from the beginning, you should not be surprised. If I just give you the algebras of the Qs and never told you anything about anything else, then you're surprised. And then the claim is that what happens if I add a mass term? So if I add x squared, well, x squared breaks the symmetry between the Q2i's and the Q2i plus 1. It actually brings in something that's outside the algebra even. And that's usually how you build the gap and how you give a mass to the X particles. So the claim is that by projecting onto this set of variables and telling you that you're only allowed to use the Q's, you're not allowed to gap the system because you don't have access to the operator that will do it.
Okay. Okay.
So yeah, this is the statement.
And then the other thing that I was wondering, is it something that you've looked at, or because from this construction, I think it's possible to fermionize these staggered bosons.
Well, it's not simple because when you fermionize things on a lattice, the Hilbert space of fermions is always finite dimensional, and the Hilbert space of bosons is always infinite dimensional.
Yes, I mean, okay, on the lattice, just in the infrared, but
right. So I haven't tried fermionization tricks in here.
Okay.
So
okay.
I don't know how to do it. I know other things that are like fermionization and bosonization, which can be more easily done with the other variables, with this. If you do use these k variables, because the k variables already have a discrete Hilbert space, when they commute between different sides, you can use kind of Jordan-Wigner type transformations to fermionize the system and then pass to the fermions. So at least for icing in a transverse magnetic field, this is the standard Jordan-Wigner, and that's a fermionization, and there you can do it.
No, the reason I'm asking is because if I just think about, you know, Lattice and Lieb kind of bosonization,
yes.
Then the starting point on the bosonic side is precisely, you know, these one-dimensional chiral massless bosons, you know, this you know, famous statement in one of their papers, something that's supposed to commute but doesn't commute, kind of sounds like the staggered boson, the staggered or this commutator that you impose at the beginning. So I was wondering if we fermionize, if we don't just get the normal fermions that Lattice and Lieb got, but
okay. So there's other constructions. So if you start with the XX model, in the XX model, that's equivalent to 2 fermions. And there, if you generalize to these n by n matrices, you get something similar. And then you start seeing in that case that there's 2 ZNs in there that commute with the Hamiltonian, but they don't commute with each other, and that gives rise to projective symmetries. So there is some story like that, but I haven't worked on it enough because it's a different class of Hamiltonians than these ones that I've been presenting. They're closely related, but not the same.
Thank you.
Okay, I don't think there's any other questions.
Maybe I can ask a quick question.
Yeah.
David, one quick question. So I'm wondering whether there are any constraints on the total number of supersymmetries you can have. I mean, for the case of Kahler Dirac fermions, I believe on a lattice of d spacetime dimensions, you can have 2 power d supersymmetries. So in this case, is there any upper limit?
Yes, actually, I have one, and then with a little bit more work, one can probably set up systems that have 2 supersymmetries. But if you actually look at the literature, Kahler Dirac in 4 dimensions, it's n equal 4 SUSY already.
Right. Yeah.
And so in low dimensions, you can play more games. In high dimensions, you're kind of stuck with one copy, pretty much.
Yeah.
And I have no idea how to do actually the gauge multiplet in this formulation. So I don't know how to do gauge links and gauge fields. I know how to do matter. And matter is kind of interesting, but it doesn't matter very much because it's not a gauge field.
All right. But I think well, let me not assume that there are no more questions. Are there any other questions? Okay. In that case, David, thanks a lot. Sorry for the technical trouble in the beginning. Thanks a lot for agreeing to give the talk, and hope to see you sometime in South Africa again.
That's very good. Take care. Bye,
Okay.
everyone.
Bye.